Okay.
Can I answer some comments? Or
Yep.
are you in the middle of a
Go ahead.
call?
Nope.
Where's everybody? 3, 6, 8. Okay, just some thoughts I had on listening to this. First of all, IP address space, 4 bytes. How many addresses is that? 4 bytes?
4 bytes.
It's 32 bits. How many addresses is 32 bits? Huh? 2 to the 32, which is 4 billion. So there's 4 billion IP addresses. Well, as you know, there's 4 billion nodes on the internet. We're out of IPv4 addresses, essentially. So we're moving to IPv6. We'll talk about that later. Ethernet addresses, 48 bits. How many addresses? 2 to the 48th. I assume nobody knows what that number is. I looked it up. It's like 278 trillion Ethernet addresses, which is why every device can have a globally unique address, just printed into silicon. At least with the population, it's 278 trillion, which point we get a bigger problem.
You lose 2 bits.
You lose 2 bits.
Yeah.
Okay, so it's still big,
Yes.
very big.
Very big.
Right? And well, I might as well say it. So IPv6 is
128 bits.
128 bits. So 2 to the 128 bits, I don't remember what that number is, but I spent an afternoon just trying to get my head around how big that is. It's trillions of trillions. It's like hundreds of millions of trillions of trillions. The IU allocation of IPv6 is equal to the entire current Internet v4 address space, at least.
So just a 64-bit block?
Maybe a 32. I don't remember. I'll look it up.
Yeah, I have to look it up. I know it's a 32, but
32 bit.
it's 4. So IU has 4 billion IPv6 addresses allocated to it.
Because there's
And
so many.
Your first reaction is, isn't that awfully wasteful, and aren't we going to regret that someday? No, because there's like 10 trillion of those to hand out. I mean, the numbers. I mean, it's hard to get your head around just how big those numbers are. Okay, DHCP. There's additional packets. There's actually 4 packets. I need an address. I have something I can offer you. I might hear from more than one DHCP server, so only to one of them do I reply, I accept your offer, and then it sends an acknowledgement. And the first one, and as far as I know, the first one wins, although you could write your stack in some other way. The first one I hear back from wins. And the other thing about DHCP is, what's standard about DHCP is how you request an IP number and how it replies, but not how DHCP works. You can do whatever you want to allocate that IP number. So you might have a list of MAC addresses and say, every time I see this MAC address, I'm going to give it this IP number. You could have a list of MAC addresses that you refuse to give IP numbers to. You could do whatever you want in the back. And so, like IU has a custom thing that we do, which is part of our sort of security system, so to speak, loosely speaking. But the point is that the standard of DHCP is how you request and how it replies, not how it determines what address to give you. Obviously, it has to give you an address on the network from which you're requesting. They can't just give you some random number, because then your router wouldn't route it. And the other thing I just want to say in general, because maybe this is obvious to everybody, every network device has state. Ethernet switches, routers, firewalls, intrusion detection systems, they all maintain state. State is always a security threat. There's always a way to attack a system that maintains state by overloading the state, typically.
So let me give a realistic example.
That was my last comment.
Oh,
Go ahead.
how convenient.
Yes.
So you can write some software on your computer that will manipulate its source Ethernet address. So even though it's hard-coded on the card, the way that really works is when the card is initialized, the software driver for that card reads the address from the card and then puts that in the packet. So that software can be modified to put a different Ethernet address in the packet. So you could, on this computer, make that a different address every packet and send out 10,000 packets per second. This table might hold 10,000 would actually be a pretty good sized table. So you can overflow this table in a second of traffic. And the process of updating this table is slow. When a packet comes in and matches this table, very fast. very little CPUs involved. But when the switch sees a new address not in the table, that's hard. The switch CPU has to do a lot more work. It's much slower. So if I'm sending 10,000 per second of something that takes up a lot of capacity in the switch, something's going to break. Now, typically on a switch, what breaks is that will cause either the switch to stop forwarding packets, depending on the design, or the switch to flood every packet, depending on how it's designed to fail. So as Tom said, anytime a device has state, that's an attack vector. In the case of an Ethernet switch, you can easily take down an Ethernet switch. You could do it right in this room right now. You could write software on your laptop and take down, if you plugged it into a wall outlet, you could take down a significant part of the building right now with just software.
Yeah, and you just download the software, you don't have to write it. So the other thing to keep it simple that Steve left out is, and I don't know how this works exactly, but there's another column here which is some kind of timeout function.
Right.
Age, I don't know how it works exactly, but some indication of when, how long ago I learned this, and it will age out.
Right, so to keep the table small,
Exactly.
right.
Exactly.
To keep the table small, these will age out. And in fact, that's a trade-off.
They
So-
store an aging time and they check again. So if the packet is sent, then it gets restarts, yeah, or like the time again starts.
Right,
If
exactly.
not, then,
So when a packet's looked up successfully, it resets the timer.
yeah, exactly.
And if the timer expires, the entry's erased, and
Yeah.
that slot is available.
Right.
And that's how they, and how long that timer goes is a trade-off between, remember, putting something in there is hard, also taking something else hard, not as hard. And so that the length of time is sort of an engineering trade-off when you're writing a switch. If you don't have very much of this memory, you might make the timer shorter.
Right.
If you have a lot of this memory, you might make it longer. By the way, here's another thing that's important to know. This special memory is a power hog. It takes much more electricity than regular memory. And it's also expensive to make, and you cannot make it really big. You know, we have gigabytes of stuff in our laptops and many gigabytes on our servers. This memory, you can't have that. You can't make it that big. We're gonna,
So I've got a bunch of comments here. So if you have some kind of age column and somebody is sending you these bogus MAC addresses and you start filling your table up, when your table fills up and you get one more bogus address packet, what do you suppose happens? I don't know, but I suppose the
It
oldest
floods.
one gets knocked off.
no, most switches start flooding.
Yeah, but I bet they also knock off that old one. I know they do, at least, well, I think they do. And then the oldest computer isn't like known about.
Right, but it'll flood then.
Right, it'll flood. So we had a circumstance, this is a little while ago, where we just happened, the architecture at the time was the TCAM limit on the 64K, TCAM limit on the 6500.
Are you talking about the ARP association table
Yeah.
that was, yeah, so that's different.
That's not TCAM.
No, it's not TCAM and it's a different
Okay, so
problem.
that was not relevant. The other point I want to make, when we talk about line rate, that's worth pausing for a second and thinking about what does that mean? So if these days we have a 10 gigabit per second switch, how many packets a second is that? Well, it depends on the size of the packet, right?
So they design, when somebody says they have a line rate switch, they mean a couple different things. Let's say the switch had 4 ports and each port was capable of 10 gigabits per second. Well, how many packets in 10 gigabits per second? You assume that it's the smallest packet. So you've got like a 60 byte, roughly 60 byte packet, and bytes, 10 gigabits per second. You gotta remember that those are 2 different measurements, 8 bits to a byte. You do the math and you find out how many hundreds of thousands of packets per second can fit on 10 gigabit. And if there are 4 10 gigabits, then a non-blocking wire rate switch would have some sort of backplane that could handle 4 times that many packets at the same time. So that's, when you've got a switch that's handling, it's really amazing, partly because I'm old. You buy these little switches at Best Buy that are 8 gigabit ports, all running at wire speed, and that little switch can forward like 1 million packets a second. And the reason it can do that is because of these tables. This will become more interesting when you guys get to OpenFlow.
Yeah, I remember when I was new to this, admittedly, that is like ancient history, but we were looking at the campus network was like 10 to 100,000 packets a second. And we were like buying some new equipment that could actually do 100,000 packets a second. And I go, gosh, Steve, you think we'll ever get to the day where our routers will do 1 million packets a second? And he goes, yeah, probably. Well, that's like laughable now these days. I have no idea what it is now, but it's a lot more than that.
So you OpenFlow project people, you're going to have to explain all of this with OpenFlow. And you get extra credit, like this doesn't mean anything in this class, but there is an obvious way to do this in OpenFlow that's wrong, and there's a less obvious way that results in the correct switch behavior. If you can figure out both, that'd be great. And I'll tell you a secret, when I teach OpenFlow, and I teach how you do this in OpenFlow, and I work through the class that had some background in OpenFlow, every single time they do the wrong way first. Even if I'm teaching network engineers. In fact, the more expert somebody is with how a switch works, the higher the guarantee that they will get it wrong. So when you guys are doing this in OpenFlow, this is the behavior you need to mimic with OpenFlow. And there's a wrong way to do it. Everything will still work, but packets will flood that don't need to. And there's a right way.
So I apologize for all the questions, but
Don't apologize. One more question.
So other than the attack vector that we discussed earlier, why is it necessary to have a TCAM table that is larger than the number of ports that the switch can service?
So the TCAM table is let me back up a second. I'm drawing a really simple picture where there is a single computer on each port. But in reality, there can be a number of things that really change this. So if one of these, instead of this being just a single computer, it was a server with a bunch of virtual machines in it, let's say 100 virtual machines. Each virtual machine would present a different MAC address. Okay, that's one example. Another example, maybe this switch is sitting at the core of the building. And maybe it's interconnecting other switches that are in the building. So you could have switches interconnecting other switches. In which case, if this was in the core, the middle, and there were a couple thousand devices in the building, the core switch would need to have the capacity for all of those. Now imagine this switch is in the middle of campus. It might need, if you were doing layer 2, which we don't, in the middle of campus, it might need to have 100,000 entrants. So this is this oversimplistic case where one device per port, but you can have one device that has many MAC addresses, in the case of VMs and a server, and you can have a cascade of switches. And as you get closer to the center of that topology, that switch needs to have the capacity to learn all of the MAC addresses.
Can I have a quick comment? This was the topology at the computing center where there was lots more computers on the same wire, like 50 or maybe 100. And it was a wire, a coaxial cable that was under a raised floor. And if there was ever a break there, everybody's down and you don't know where the break is and no easy way to find where the break was. And so we would like break it in half and make 2 cables out of it. If this half worked, then we knew it was over here. And you just kept going by raising floors, grabbing the wire, doing stuff with it. I mean, it could be, 2 hours, an hour to 2 hours for us to figure out where the problem was and fix the problem. In the meantime, all 100 nodes are down. So that's the other thing, when the switches came in, it's like, hallelujah, we're never gonna have to do that again, because if there's a wire break, it's just taking down one computer, and it's pretty obvious what wire is broken, so that's ancient history. The other thing, and maybe I'm wrong on this too, but if you have this timeout column here, at least theoretically, maybe this almost never happens, but this is an example of understanding how stuff works to troubleshoot the corner cases. So I can at least imagine a case where, for some reason, traffic is flowing this way and there's no packets coming back, like a UD, will you watch
Yeah,
it?
don't go there.
Don't go there?
Yeah, because I'm gonna talk about that later.
Okay, then that has implications that we'll be talking about later.
I'll talk about a pathological case in the data center that caused a big problem. And understanding how the switch works, and sort of what Tom was getting at, made the only way to troubleshoot the problem is understanding how the switch works. The level we're explaining it. Actually, you're next. Did you still have a question? And then-
Oh, I was curious about the difference between the TCAM and the CAM. Did you fully?
Yeah, so old switches used to have content addressable memory, and so far everything I've described would work with content addressable memory. Content addressable memory lets you say, here's the MAC address, in one clock cycle, tell me what port to send it out. TCAM allows you to mask the address. In other words, say certain bits doesn't matter what they are. So here's an address, and bits 5, 7, and 8 don't care if those match or not. Those are wildcard. And so TCAM has the ability to do wildcards, which we'll get to why that's useful.
Okay.
Actually, in the OpenFlow case, it'll be real obvious.
I was almost the same question. What means T in TCAM?
What is
T and TCAM.
ternary? Ternary.
Okay, but I confused TCAM or CAM. It's only the name of the table.
TCAM and CAM are a kind of memory, a kind of random access memory. And they have a special property. And that property is they'll support, if you give them a value that's stored in them, they will tell you what row that value is stored in. So then if I know it's row 2, I can look up and see what the port number is. And the TCAM memory is made physically different than the conventional RAM that you might have in your laptop or computer.
I mean, normally, you say, give me the contents of this address in memory. But here you say, I need.
Tell me the address of where this content is. So opposite of the way memory normally works. So here's some content you're storing in memory. Tell me where it is.
Ternary means composed of 3 parts. So there must be 3 columns, the address and the port and the timeout, is that way?
The mask. No, timeout's not actually in the TCAM table because it doesn't need to be. I lost my train of thought. So you should really know this stuff cold. This is described in detail on the internet. You run into switches all over the place. And knowing how the switches work at this detail is critical to troubleshoot lots of problems. And you know that I hate to say it, but I know a lot of network engineers who actually don't know how this works, or at least in enough detail that they can troubleshoot problems that crop up at this layer. So, you know, if you get nothing more out of this class, and you're doing anything with networking, and you really know how this works, you're you know, that's a cool thing that you will find useful, I guarantee it. Yeah,
I don't think I had a question,
Okay.
but if I just wanted to, since you did call me, if you, if I did just want to research different types of switches, how should I search that? Should I just say?
So if you search on Ethernet switch, Wikipedia, I'm
Okay.
sure has a really good entry because you know geeks write Wikipedia articles, which means that the network geeks will write the Wikipedia articles. You also find TCAM in Wikipedia, and it'll probably refer to CAM and describe the differences. DHCP, I know, is detailed really well in Wikipedia. IPv4, with these 4 bytes, with the 4 billion possibilities that we're running out of, detailed very well in Wikipedia. Ethernet, the whole frame, not just the source and destination address, absolutely good in Wikipedia. IPv6, this version of IP that supports 128 addresses, more addresses than there are atoms in the universe, I believe. Also excellent in Wikipedia. So, you know, a lot of this class is going to be us helping you understand things that were difficult to get out of the reading. The behavior of an Ethernet switch, the behavior of an IP router, those can be pretty challenging to tease out of an article on them. And we're going to go over those things in detail in class. But if you want to get the most out of this class, you know, show up with questions. I don't get how this works. Sometimes we won't have any answers, but we've done this for a long time, and you know, chances are we can help you out in discovering that stuff and sort of completing this picture of how networking works. So I have a question. Is this what you guys hoped the class would be about? Yeah? Okay.
Reading, IU libraries, go to libraries, iub.edu, search for books 24. There's this thing called books 24/7. This is essentially thousands of online books, and they're by categories, and so there's like IT, and there's networking, and there's like hundreds of books in there. So if you want to just go to a standard kind of book about networking, there's hundreds of them available to you at no charge via the IU library site at books 24/7.
I will tell you, most of the articles you'll read about Ethernet switches won't tell you how they work inside. They'll tell you their behavior. They'll talk about flooding and unicast forwarding, but they won't tell you frequently how this table works and how it's populated. And this is really important. We'll get to, I'll have it ready for tomorrow, a pathological case that Tom started to get to that took our entire data center network down for hours. And somebody who understood this in detail could see from across the room what the problem was just by looking at the lights. And that's, you know, understanding how this works in detail can differentiate you from other folks and give you some skills in terms of troubleshooting that can come in real handy. So it's a couple minutes early. Any other questions about Ethernet switches?
What should they do for tomorrow?
So I introduced this, how a switch works. You need to know how a switch works because we're going to talk about a complicated example of how a switch works in this case where things look very bad, wrong. And I'm going to tell you symptoms, and I want you to figure out what's wrong. So the first symptom I'm going to tell you is walking into the data center. There are all these switches, and they all have a light per port, and that light flickers every time a packet goes out that port. And when somebody walked into the data center, they saw all of those lights flashing at the same time for the entire data center. So that was the first symptom. And we'll tell you more about more symptoms. And if you know how the switch works, you should be able to identify what the problem is, sort of. There's some extra stuff that we'll help you with.
So if you look at on-course under assignments, there's 2 things for week 1. The first one is just here's a bunch of concepts we're going to follow in some order and some reading so you can start reading ahead. But I don't know if we're going to get to everything this week. The other thing is week 1 concepts additional list. That's actually the one you need to look at. That's what we hope at the end of the week, in just a couple more hours, you know what all those things are. And so those things, I would say, start with those. If you don't know what VXLAN is, and I suspect most of you don't, start reading on what VXLAN is and so forth. So look through that list, but it's also got ARP and IPv6 and IPv4 multicast, and some of you may know what those things are. So check out that list first, which is called Week 1 Concepts Additional List.
So, and start at the top, and if this is, it shouldn't be too much. This is an accelerated course, it's only 6 weeks. But I do want some feedback on how far you got down the list. And different people will have gotten different, I think that's fair. It's a pretty ambitious list, if you already have some background. Those of you who have background ought to get through the whole list. So, anything else? Cool, okay. What are the 4 things that you're gonna get your grade on? You're all gonna get A's, right? What are the 4 things? Attendance, participation, we're gonna talk about a paper, we might talk about it tomorrow. Poster session, okay? You do those things, you know, you put some effort into it, you're gonna get an A. Can't show up, let us know, okay? All right, thanks.
What's your name and email again?
It's P. Westner, WESNER @indiana.edu.
Okay.
I